All right, recording started. Welcome, everybody. Thank you so very much for joining us. It's great to see this crowd here today, joining us for an anticipated amazing talk by Jeff Linderoth. So let me just briefly introduce him. So Professor Jeff Linderoth is the Harvey Spangler Professor in the Department of Industrial and Systems Engineering at the University of Wisconsin-Madison. He also served graciously as the department chairperson from 2016 to 2021. Professor Linderoth holds a courtesy appointment in the also computer sciences department, as well as a discovery fellow at the Wisconsin Institute of Discovery. He received his PhD degree from Georgia Institute of Technology in 1998. He was also previously employed in the Mathematics and Computer Science Division at Argonne National Laboratory with the optimization-based financial products firm Axioma, and he was also an assistant professor at Lehigh University before he came to Madison. He has a bunch of awards. I'm not going to name the whole thing, but maybe more recently, his awards include an Early Career Award from the Department of Energy, SIAM Activity Group on Optimization Prize, as well as Inform's Computing Society Prize. And in 2016, he was elected to be a prestigious member of Inform's Fellows. And the last but not the least, he put this as the latest update in his CV, but the most important, I would say, in 2010, he actually won the Stochastic Programming Tennis Championship. And yeah, it's my great pleasure, Jeff, to host you here, and please take it away.
Well, thank you, Mariva, and for COSP and for everyone who's organizing this wonderful seminar series, and especially for the invitation. I'm excited to tell you about some work that I think is actually pretty interesting. I don't often say that about my work, but I actually do think this is somewhat interesting, and especially to this community. I hope it'll be interesting. It was done as part of the PhD thesis of our talented student, Sichao Ma, who has left Wisconsin and started work at Disney. And it was sponsored and have collaborated with by ExxonMobil Research and the scientists there, Logan Matthews and Young Dae Kim, who was a UW-Madison alumni from Mariva's time, essentially, I think. Okay, so I have to begin my talk with a bit of an apology in that I feel a little bit, oops, I have to go over here. Lots of apologies. I feel a little bit embarrassed that I haven't invested the time yet to make this talk as humorous, I think, as I like to make most of my talks. And so it's a little bit more technical and mathematical, more equations than jokes, but hopefully you'll find the technical content interesting enough if to pay attention, even if the humor doesn't capture your attention. I guess I'll say I am trying to, I think we're all getting better at doing these teaching online and doing those things. So I do have an eye on the chat if people want to interrupt with questions if things aren't clear. Or maybe our hosts can interrupt me, or you could even just speak up because it's a small and I see very friendly group of people here. All right, so here we go. So we're going to set the stage just with a little bit. Let's do a little bit of warm up before we get into the real meat. Let's just sort of set some notation. This community and this crowd won't need to be told what is a two-stage stochastic program, but it's just setting some notation where, and in this case, we're going to be solving two-stage stochastic mixed integer linear programs where we'll have a linear objective function of some first stage variables y, and then the ubiquitous and common recourse function where given y and an outcome of a random variable c, we solve an optimization problem to determine the best recourse. And we want to solve the problem then, of course, that maximizes the cost we pay now, but maximizes the cost we pay now plus the expected profit, say, we can get overall outcomes, right? And I guess important for this context is that this methodology, we've been primarily working where both y, the set of first stage decisions, and although not in all of our computations, but the methodology works, and in some of our computations, the set z will be mixed integer sets, so integer variables at both stages. So, this two-stage stochastic information flow, two stages, is we make some decisions, nature reveals herself to us, and we react. Okay, but now I have a I have a hot take. I think every good talk should start with like a hot take or a controversial opinion. And especially for many of the people working in this, and many people on this call, I hope I don't get attacked or hung up on by sort of saying this. But I mean, it's not controversial to say that the whole concept of decision-dependent uncertainty is a super hot topic in stochastic programming. And the way in which I described the two-stage stochastic program, that random variable Cassie was what people would call an exogenous random variable that was independent of anything else. It was something that we had no control over or anything like that. It just existed outside of the decision-making process. But I somehow feel like I don't actually believe in decision-dependent uncertainty. Like somehow, like morally, I feel like the world is just somehow random, right? And I think it's just a matter of I don't like the term. And like I think when people say decision-dependent uncertainty, it's certainly a very useful way to model this world that could be random. But somehow morally, like when we started thinking about this, it seems like there just is some underlying the world is random, right? And we interact with our random world, and we potentially learn about it. We learn things about our random world, but it doesn't seem to me, maybe it doesn't, the process doesn't seem very random if somehow you're not unable to change that process. So that's sort of my hot take, is that I don't believe in decision-dependent uncertainty. Don't worry if you submit papers to journals. I was not a referee who's seen any of these papers or commented on them. I haven't refereed papers in this area, so I'm not rejecting your papers because I don't like this concept. But I'm not saying I don't like the concept. I think it's just an interest. It's just I have a different way of viewing, say, the world, which is sort of fits in with how we're going to be modeling sort of this extension of a two-stage stochastic program that has what some people would call, and many people have called, decision-dependent uncertainty. Okay, so we're going to sort of just think of a different, and it's actually sort of a simplified version of probably what people would call decision-dependent uncertainty. But what we're proposing, which was sort of like we think a very reasonable model for this complicated problem that ExxonMobil is facing, is that we have the option to like learn about this random variable, this random process Cassie, and we do that in this context by just taking certain, and these cases are very discrete actions. Either we do something or we don't do something. We call that probing, okay? And so in our world, or in the model that we're going to be proposing here, is there really two key components of the model. So first of all, there's in this case, an n-dimensional random vector eta, okay? And we are going to be able to observe specific components of eta. Those are going to be like the probing decisions that we're allowed to make. And this random variable eta is jointly distributed with Cassie on the same probability space. All right, so eta is on the same probability space as Cassie. So that's the first component. We have an eta that we can probe. It's jointly distributed with Cassie, which is sort of, say, the real randomness of the problem. And then it costs us something to probe, right? So for any subset of the components of eta that we probe, we have to pay something, which we probably seems reasonable to assume that the more you probe, the more you pay, right? So we sort of assume that it's monetary. All right, so that's sort of what the probing is. And now we have sort of a new information flow in that now the decision problem that we want to make first is what components of eta would we like to probe? So we're going to choose a set of components S, and then I can observe eta S. And now, because I have more information, right? I observed eta S, my decisions that I'm sort of making, I don't know, what used to be stage one, or right now in the two-stage problem, they can, of course, depend on eta S. And then the distribution I'm going to observe, right, is now the conditional distribution of the random variable, given that I've observed eta S. So I observed the S components of the random vector eta. I'm going to get this, and then I can sort of have a final recourse. right? So really the question here, the trade-off, and this is what ExxonMobil sort of gave to us, is like, okay, now our decisions why that we had to make, say, with no information before, now we can have them depend on some information, namely what we've observed or the S components of this random vector eta. And so can we do better than if we had observed nothing? And moreover, does the amount that we do better, is that offset the cost of probing, right? That's the game that we'd like to play, or the problem we'd like to solve. So in the let's say unclassified, or in the unclassified examples, or the examples, computational examples I'm going to show you later, we have a stochastic facility location problem that we've sort of set up to sort of fit into this information flow framework, in which you can sort of think of it as like you can potentially decide some market surveys to do, or areas, maybe even if you want locations in which you're going to do market survey of demand for a particular product or products, and then you could observe, the outcomes of those market surveys. Are them going to be that's a good question. Yeah. So if you probe several times the same uncertain parameter, no, you do not see the same thing, right? So eta is a random variable. So you're going to see one outcome of that random variable. We haven't yet thought of the extension about, oh, what if you want to probe twice to reduce the variance maybe of what you're doing? But yeah, we only observe one, great question, Phoebe, one outcome, right? So this is why I'm trying to I should have maybe said that in, I'm not sure I always do it, but what I'm trying to do is it's always confusing to me whether you're talking, when I read stochastic programming papers, maybe I don't read enough of them. It's always confusing to me. Are we talking about the random variable, or are we talking about a realization of that random variable? So I think we try to use bold most cases when we're talking about the random variable. But here it's not using bold, because this is what I observed, right? So I'm just observing one outcome of that random variable. But that's a great question. Maybe, and even in some of the application context, actually, like the second one I'll show, I was like, I don't even think it might not even be possible to observe the random variable more than once, maybe because it somehow it would be physically impossible. But anyway, I guess you could certainly do it in this context, but there is going to be some uncertainty in the survey results you get. But based on those surveys results, then you have to set up your supply chain, or whatever it is. You have to figure out what facilities to build, essentially, and sort of size the facilities and figure out where to put them. And then you're going to do that knowing at least something about demand, because hopefully, assuming, I guess this whole setup only makes sense, right, if what you observe, eta, has some correlation. It certainly is not independent of Cassie, right? Otherwise, this is all kind of pointless or useless. So hopefully, you're gaining some information there before you make your final decisions, after you've opened facilities and then, I guess, serve customer demand to meet profits. This isn't the real application that Exxon cared about, of course, and this is actually a few people in our community have worked on problems for ExxonMobil, kind of working on this exact problem. They had a different way of modeling it. But here in the ExxonMobil context, they want to decide how to run, say, long-term, large-scale operations of a resource field. Think of like natural gas and oil under the ocean somewhere. And so what they need to do is figure out, they have maybe some, they buy these reserves, or countries have these reserves that could be developed, but in order to develop them and maximize the profit, they need to know, they'd like to get a better handle on how much resource is actually there. And they can do that by doing some actions, which is sort of doing these sort of complicated and actually very expensive geological surveys, or actually drill some tentative wells or things like that to figure out some information. And from that, they get an idea whether this whole thing was a big dud, or this is a huge profit, could definitely very resource rich, things like that. And so then based on that, they have to make multi-billion-dollar decisions about how much like floating capacity they want to install, right? And so and that, since this is a very expensive decision, they want to make sure they get this right, but also deciding what to probe is also very expensive as well. right? So given those two things, then so they install the resource capacity and decide where to put it. They get a realization of the random variable given what they've observed, and then they maximize profits. Okay, I should probably. Anyway, everybody understand the context? Anyway, those are the applications. I can go slow, and I'm definitely going to stop at 10 o'clock because I have another 10 o'clock meeting. So at a certain point, 10 o'clock my time, I should say. Nobody else is probably on Central Time. But speed up a little bit if I have to. Okay, so that's the context. And then, so we're just setting some notation. We're sort of going to introduce like the main takeaway. This is like, we're going to call this thing, what Merva calls a 2.5 stage stochastic program with these sort of discrete actions at the first stage that allow you to understand the things about potentially the conditional distribution. A probing enhanced stochastic program. So for any subset of the components you could probe, and for any observation you might see from those subset of the components, there's kind of like a conditional, well, not kind of like, there is like this conditional recourse function, right? So it's just sort of like the regular recourse function, except now it's going to be the recourse function conditional on what you observed, right? So this is, and then but this is just for one of the potential outcomes we could see, right? So what we really want to do is optimize the expected conditional recourse function, which is the expectation over all of the possible things you could see of this conditional recourse function, right? And so that's we want to trade that off, right? So this is like tells you the information that you could get by probing in the long run, how you would expect to do if you probed the S components of eta, and then this is how much you pay for probing the S components of eta. And this is what we want to maximize. So we call this a probing enhanced stochastic program. Okay, so I'm 19 minutes into my talk and I've gotten to my outline. So I can tell you what we're going to talk about. So, I mean, I at least have introduced, this is sort of, I wanted to spend a little time at the beginning of this to sort of say, here's the context. And I think this is a useful way of sort of thinking about the problem with this, decision dependent uncertainty. So I'm going to tell you two ways to try to solve or get approximate solutions and bounds on solutions to these problems. One, which has appeared already in the literature by other people, which is sort of what is to sort of write a non-anticipativity based, I should be better at saying that word in this community, non-anticipativity based MIP formulation. And sort of our new approach, which is based on just sort of a different relaxation based on information sort of theory, or just information relaxation, sort of perfect information type bounds combined with branch and bound. And then, of course, we're never going to be able to sort of enumerate the support of the random variables, so we're going to have to combine these with sampling to get, and a focus of our work was to get good solutions, but actually also to get provable statistical bounds on these very complicated problems. Okay, and then I'll show some results. I can, if I have time. Well, I will show you some results. I'll talk more. I'll skip parts if I run out of time, but I think the results, I want to get to the computational results. Okay, so here we go. So this is sort of this is how when we teach stochastic programming formulations, like even for two-stage problems, I don't know how maybe different people do it different ways, but like there's sort of the tree-based way, I call it, and the non-anticipativity based way. But so the non-anticipativity based way, even a two-stage problem, is you just split the variables. You allow there to be a different decision y for every possible outcome eta, and then you enforce non-anticipativity of those first stage decisions. All of your y of etas have to be equal. This goes back to Betts and everybody, Allen and people like that, of course. But in this context, right? Oh, I should say also, yeah. So if you don't enforce the non-anticipativity constraints, if you're allowed to cheat, right? That's what you're doing, is you're allowed to sort of make a different decision y, have this function be not measurable, different decision y for every outcome eta, and then you take the expected value of that, you get the perfect information bound. Okay, so we're going to be using that as part of our bounds. But in this context, right, we don't really have the basic NA formulation, right? Because we can observe part of eta, we don't actually need all of the y's to be equal, right? So the new formula or the recipe for building this non-anticipative MIP formulation is again to split the variables, allow a different decision y for every outcome of eta, and we have to enforce observation-dependent non-anticipativity. Namely, if two random variables eta prime appear identical on the components of the random vector that we observed at those components S, then we have to have y of eta equal y of eta prime. We have to have, that's how you enforce non-anticipativity for this to actually be like an implementable policy, if you will. Okay. So how do we do that? So this is the first thing that Ignacio did with his students, goes back, I should know this, like at least 10 years, but I think even more now, is you can for any subset of the variables that you decide, of the eta variables that you decide to probe, you can look at all of the pairs of outcomes of eta that appear identical with respect to S. That's just sort of a shorthand way of saying they're identical on S, right? We introduce some integer variables to decide, to declare indicator variables on whether we probe the component, right? And then we just write down on this non-anticipative formulation where we maximize I guess this should probably have a negative there because I assume alpha is positive. So I think I'm missing a sign there. But so there's a cost of probing the X and then the expected value of both the decisions that we make, sort of the old first stage, now second stage decisions we make, plus the other decisions. And we need this strange constraint. So Y has to be feasible, Z has to be feasible in some sense. But then this is sort of the strange constraint, namely that if two scenarios appear identical with respect to the set of variables we probed, then we have to make the same decision. So this isn't a MIP formulation. It's a formulation because like the variables X sort of appear as part of the for all here. And so with Ignacio, under some sort of mild conditions, namely if the set Y is bounded, for the integer variables, if the set Y is bounded and the etas sort of have some minimum distance between them, if they're different, then you can write a whole like MIP formulation using big M's doing that, enforcing that constraint that if two scenarios, eta and eta prime, appear identical on S, the things that you probed, then you have to make the same decision. So you could kind of see that this does that, right? Because you just sort of, if this is some giant enough big M, but if this thing is all zero, then they have to be the same, right? Any questions? Anyway, so this is fine, but like there's a few things that aren't maybe so Alan's got a better solution. But anyway, we'll sort of look at thank you, Alan, for sending that in. One problem with this, I mean, besides people often don't like to P almost every sorts of things, but just imagine these are all finite, discrete distributions. But the number of constraints here is sort of like on the order of the support of eta squared, right? Not just eta or something like that. So this is sort of undesirable, I would say. Which for sort of some small examples that we were running, this was the first approach that we actually tried. And if you have like a small problem, I think this has 10 this was 10, eta was the components of eta you could probe were 10, and each of them only had two outcomes independent, 0 or 1, sort of Bernoulli. This is the size of the problems you get, right, for this MIP formulation. So this is not scalable. Okay, so the second approach I want to tell you about is kind of a very, I think in retrospect, a very simple approach. And if people have done this, I would like to know that. The papers submit, but maybe the referees will tell us that this has already been done, but we couldn't find this approach exactly in the literature for this problem. So recall that this is our probe and enhanced stochastic program, and this new approach is sort of based essentially on sort of a very simple property that sort of knowing more is always better. Simple lemma that sort of says if you probe more components, if T is a superset of S, then you always have to get a larger value of F, right? And so specifically, we also are assuming that alpha S is non-negative. It always costs you to probe something, right? So if I probe everything, right, this is an upper bound on the optimal solution value. That's in fact if I probe everything but don't pay for anything, that's precisely the perfect information bound. But if I probe everything and pay for everything, probe all the components, then that's a feasible solution, right? That does not violate non-anticipativity. All right, so we get an upper bound by Bernardo asked a question. Quick clarification. No, we probe coordinates of, sorry, it's actually the opposite. We probe coordinates of eta, and then we observe Cassie given eta S, given the eta that we observed, conditional on that, because that will give us that information. Okay, great questions. Okay, so these are very simple, sort of obvious properties. Okay, and so that gives us I'm an integer programmer by training. I have a lower bound, I have an upper bound. They're not equal often, sadly. But what do? We give up and we start branching, right? If we can't think of anything else, then we're going to start branch. So we sort of devise a scheme to sort of improve, because iteratively improve these bounds based on sort of either enforcing that certain components must be probed or cannot be probed. So the one branching idea, right, is sort of the most natural one, is every node of the branch and bound tree will have precisely, will have two subsets, some components that you have to probe and some that you don't have to probe. And this is probably way too complicated of a formula. But again, the bounds that you get sort of are just the natural extensions of the perfect information bound in this context, right? So to get the upper bound, you probe everything you possibly can, everything that you didn't fix to 0, but you only pay for the things that you were forced to fix to 1, that you were forced to pay for. That gives you an upper bound on the optimal solution value, because you're cheating, because you probe for everything you hadn't fixed to 0. And then the lower bound you just get by paying for everything that you probe. So that's sort of what those two numbers are. The upper bound you get by this is the value you get for probing everything except what you absolutely cannot. And then this is, but only paying for the things you have, right? So that's sort of where the upper bound comes from. So the lower bound is similar. So that's one branching method. It's the natural one. You branch on one component at a time. So it'll give you a branch and bound tree. It's a very small branch and bound tree that'll kind of look like this. But an important component of things that I'm hiding, it sounds too good. Well, I don't know, maybe it sounds too good to be true. I don't know if things at this point, but I'm hiding some important components of how this method works in, well, how do we evaluate this function f of s and things like that? And that's not as easy as it seems. So I'm going to explain to you how to do that in a moment. But an important component of the branch and bound algorithm here is, note that if I did evaluate f of s, this s1, 2, 3 at this root node, and in fact, every time I fix a variable to 1, to get the new upper bound, I can use the same value of f of s. I just changed the upper bound by paying for the thing that I fixed to 1. That's sort of what happens, right? It happens all the time. All right, so that's sort of a cheat that if you assume, which we don't have to assume, it is true that the hardest part of this evaluating this branch and bound tree is evaluating f. Every time you branch right in this method, you don't have to do the hard work anymore. So that's an important empirical computational cheat. A second branch and bound method, maybe I'll skip in the interest of time since I'm 18 slides in, but you can sort of think of it, it's equivalent in integer programming to kind of like branching on subsets of variables at a time. Sort of like these are things that you definitely cannot, a whole subset of variables you definitely cannot probe. So the way we sort of organize the computation, every node will be characterized by a set of components of eta that you cannot probe, and then a set of subsets of the components of eta. And each one of those subsets in the collection of sets, you have to probe at least one of those from each of those subsets. And there's reasons why we did it that way. I'm gonna kind of skip this, but in some sense you get sort of a branch and boundary. Actually, most of the times we branch into 3 in this method. So the branching thing would be the first 2 nodes of this branch and boundary is, imagine that you not allowed to probe anything. So in fact, this node of the branch and boundary, if you understand what I've been talking about, this node of the branch and boundary is precisely the 2-stage stochastic integer program you would get if you didn't have the option of probing, right? In some sense, you don't pay for anything, you don't learn anything. This is what you can do. And in some contexts, actually, this is not an unreasonable solution, right? Sometimes the value of information just isn't there, right? So this isn't like a terrible node to do. And this node is sort of kind of a stupid node. It just says you have to probe at least one thing. But then once you have to probe at least one thing, then we keep breaking these into these 3 sets where, like, we pick a subset of one of these sets. In this case, there's only one. And then you say you got to probe at least one in this, or you can have to probe at least one in both. In some sense, that's what the branching trichotomy is. Anyway, so we have these 2 branching methods. The second one actually, the only reason I tell you, the second one actually turns out, in this context, it turns out to work a little bit better than the first. That it's a little bit more clever. So that's the reason I mentioned it. Okay, so now we get to the part where I have to tell you I have to come clean in the sense and say, okay, but now if I want to sort of evaluate a node of this branch and boundary, or even estimate or get bounds, no, we're not. Phoebe asked, are we assuming the distribution is discrete? We're not going to be assuming the distribution is discrete for the time being. While I'm telling you how we evaluate f of s, let's assume that it is discrete, because if it's not discrete, we're never going to be able to evaluate f of s anyway. We're only going to be able to estimate it probably in like all the simplest possible distributions. But for the time being, let's assume that it's discrete. And then I'm going to tell you actually how to evaluate it, not just estimate it. Okay, so now, so we're going to assume it's discrete because I have some summations here. I guess it was a perfect time for you to ask that question, right? So now to evaluate f of s, what we do is we say, okay, so I've picked an s, right? And then there's going to be, for the s components of eta, there's going to be different outcomes that they could be. Maybe there are very few of those. Maybe there's a lot of those. It kind of depends on how big s is, right? Assuming that if s is larger, then this sort of like projection onto the s components of the support of eta is going to be probably have more things in it, right? So, and for every one of those things, there's this conditional recourse function. All right, so, and this conditional recourse function is just a 2-stage stochastic program. So I guess maybe I should have started with this. Maybe I should have started, actually, next time I give this talk, I should have started with this as like one of our founding principles, at least before we started this work. I think Lutke definitely believes this. Some people may not. I believe it. I believe anything Jim tells me to, but like 2-stage stochastic integer programming is almost a solved problem for small enough number of scenarios. Like you can give the extensive form to Garobi for a few hundred scenarios, and it kind of solves. And most of the time, you only need a few hundred scenarios to be able to get a reasonably good solution. So if you don't believe that, then this whole method is probably requires a little bit more work. But we're sort of going on the assumption that like this evaluation of R of eta of S is somehow tractable, right? It's not tractable if it's a mixed integer program in any computational complexity sense of the word, but neither is a single stage integer program, right? So we're assuming this problem is tractable, right? And then, right, so this is a 2-stage stochastic integer program, but I have to solve one of those to evaluate f of s, right? Because I'm only, for each unique outcome that I could see, sort of weighted by how many times it appears, right? I have to add them all up to evaluate f of s, right? So I have to solve this many two-stage stochastic programs to evaluate f of s. That's sort of the evaluation. So that's like a non-trivial, I would say, amount of work. It could be, but that's what we do. Okay, and so of course you can never do this, probably, even if the distribution is discrete, like you saw before. Like we're going to be solving problems, even like our simplest problems, well, not our super simplest, but say we're going to have n equals 20 with maybe just two independent outcomes. So it's already 1,000, it's 1,024 elements in the support of H. And then you also have to, there's another, we don't know, actually, it depends, you'll see later, we also have to sample in Cassie as well, right, to sort of, so we always going to have to sample. And what we're saying here, actually, this is going to be interesting, we'll show you in a moment, is that it will also work for a continuous distribution, but you have to sample sort of in the right way. You have to make sure you sample conditionally. By the way, we have two sampling methods. Like one is going to be sort of, let's call it mom and pop SAA external sort of sampling, right? So we're going to do these problems, we're going to draw a finite joint sample. So I sample A to K, Cassie K from the joint distribution, and I'm going to solve that sampled approximation. And then there's an internal version where we sort of, at every node of the branch and bound tree, when I want to evaluate f of s, I want to conditionally sample based on A to S. Okay, so I'm going to tell you what those two things are, just with a little bit more detail. I better speed up a little bit. But this is really, I hate this slide probably at least as much as you do, in the sense of like, it's a little bit too, there's too much notation and things, but it is just an implementation of this, which is a little bit cleaner for the sample distribution that I just drew, right? So that we have a, for A to S, we have this sort of sampled over n conditional recourse function. So this is like, this is going to be an important thing. So like in the sample that you draw, right? And for the A to S that there's going to be some of the other scenarios that match on the S components, right? That match A to S on those components, right? So these are this is this projection. So it's this number of, on the same talk, I'll be sure you do of, yeah. So this is a very, how can we sample Eta? Well, you can't, I don't know if you can, well, here we can, we assume we know the distribution, right? So like in this case, I can sample from Eta, and I think this answers both Bernardo and Phoebe's question, which is, again, I would say a legitimate potential criticism of this method, is that like, how are you even going to get this? I mean, I guess the joint probably exists, but how are you going to get it, and how can you sample from it? So it's a fundamental assumption of our model that you have access to these things, that you can do this thing. Like I can do this. I can jointly sample from this distribution. And if I do that, then there will be, on the S, when I take this distribution and I pick an S, right, there'll be some scenarios that sort of match A to S, that match one scenario on the S components, right? And that gives me sort of the weight that I need to sort of to do this. So sometimes this is small. If this is always one, right, then I'll get to that in a moment. But yeah, so you're not putting together, so this is the important thing here, is like this two-stage stochastic program has this many scenarios in it, the cardinality of this set, right? So sometimes if this is just one scenario, then, and I'm going to be averaging over those, then it's no different than, say, the perfect information bound, right? So you sort of get some improvement if over the perfect information bound when you have things that appear to be the same on the things that you've chosen. All right, so I'm sort of losing the thread a little bit. But does that make sense? So it is just sort of like how you would evaluate f of s. You take a joint sample of size n. This is going to, of course, give you this. You can solve this problem, and it gives you this number v sub n, which is a random variable. If you assume it's, you kind of think of it as a random variable because this, if n was a random sample, an expectation, it's going to be, it's biased sample, it's going to be larger than the true bound, just like normal SAA sort of theory. That's what I guess that's what this, yeah, this is a good question. So Phoebe's already making all my points for me. You guys look in the chat. So how can you implement, actually, maybe I'll make this. No, this is lovely. Like maybe I'll make this point. Maybe I'll make this point now because it's going to be like a huge, I think it's like cool. The conditional sampling is sort of the way to do it. Is like, so Phoebe is of course extremely smart and has already sort of seen through my trickery to sort of say like, now suppose I'm doing this external sampling from an absolutely continuous distribution of eta and Cassie, then the likelihood, the probability that this set has more than one element is 0, right? Every one of these things is only going to have one thing in it, which means that the bound I get from doing the sampling approach is the perfect information bound. I can't improve on the perfect information bound in some sense, regardless of how big I sample, right? Even if I took n equals 1,000 samples, 10,000 samples, 100,000 samples, I'd be like, oh, I can't improve on the perfect information bound. So it's sort of useless to do in that context. It only makes sense if your true joint distribution is really discrete, and then you can do this method. And I mean, you can always do the method, you're just not going to get anything useful unless it's a discrete distribution. And that's exactly, she asked me all the right questions to like lead up right to the next slide where I was going to be, because this is exactly the point that I make in this context. If you have a continuous distribution, there's no way that external sampling will ever improve the perfect information bound. So you have to conditionally sample, which is what we do is we take, so we take a sample, right, of eta, just the S components, okay, of eta that we're interested in evaluating f of S. So we take a sample of S components, and then for each observation of that, we take a conditional sample of Cassie, given this particular observation of the S components of eta, right? And if you do that, you can also obtain an unbiased estimate of f of S, okay, as this, just sort of doing the conditional sampling. And again, this is just the way you would implement what I had a few slides before. It's, yeah, so in order to evaluate this f of S, right, and you do this, I'm going to take a sample of size 8, say N1 of the etas and N2 of the Cassies given the etas, right? So I have to solve N1 two-stage stochastic programs that will add up that's how many I have to add up. And each one of these two-stage stochastic programs has N2 scenarios in it, right? And so that's how we do conditional sampling. Okay, and so now we can do this, at each node of the branch and bound tree, we're doing, this is just one, sample. If we have to replicate that, this gives me one estimate, right, of this. I need to replicate this to get a statistical bound of what f of S really is, right? So this is a biased estimate. For the upper bound, it's a biased up, so that's actually good for us. We can use it for upper bounds in the branch and bound tree, and we can replicate it to get, confidence intervals or whatever you like, statistical upper bounds. And so like, and this goes back, I think Brzezinski and Norkin had an old paper that's like stochastic, branch and bound. What do you do in a branch and bound method if your bounds, the bounds you're getting are like statistical, right? Like you can't ever prune by bound, right? Because it's like there'll be some small chance that that node would be optimal. So the way we sort of get around that or implement that in our method is that we sort of never can declare victory. We just can only just keep branching until we get tired. But we always choose the node of our branch and bound tree that has the largest, say, statistical upper bound. And then when we branch, hopefully, not always, but usually if you have enough samples, the variance of your estimator is small enough, your statistical upper bound goes lower. And then if you want a true statistical upper bound, you have to look at all the leaves of the branch and bound tree, their statistical bounds, and combine them to get a true statistical bound. That's what we do. The math is is straightforward, but even messier than most of the other notation on my slides. Okay. There's a lot of more stuff that we did, lots of other cool tricks. I think that you can get, if you read the paper, that things like when you choose, how you choose which component to probe, just like in integer programming, choosing a branching variable can have a huge impact on the performance of the tree. It's also true in this, and we had some, I think, clever ideas on how to decide which component of Ada to branch on next that's going to improve the bound the most. It turned out that at least for the examples I'm going to show in computational results, doing smart sampling to reduce the variance of your estimates was like hugely important. So we just did Latin hypercube. You can also reduce the variance of your estimates in the case of if the support of Eta S is kind of small, like suppose there's only like 4, if this only is of course in the discrete case, but suppose there's only 4 possible outcomes in that projection, you shouldn't sample from a distribution that has only 4 things in it. You should probably just enumerate it precisely. And an interesting component of all of this work is, especially in for the discrete distribution, when you're doing the external sampling, I guess here external sampling at many different nodes of the branch and bound. So this is a 2-stage stochastic program you have to solve. But it could be that this 2-stage stochastic program you have to solve sort of appears somewhere as part of the evaluation of f of s somewhere else in the branch and bound tree, because of the projection you sort of get to see. You need to compute this number again. And so it was important for us to actually save those values. And I won't be able to tell you about the heuristic. I'll just tell you how great it is at the end. Okay, so it's a greedy heuristic that's not clever at all in the fact that it's greedy, but it's clever in the fact of it's sort of based on trying to estimate the value of like probing or not probing an individual component, but that requires a lot of computation. But we sort of have some clever ways to sort of quickly sort of understand the value of a local move. Okay, so in my last 5 minutes here, how do I have so many slides? I'm going to tell you about some computational results on some stochastic facility location problems with different, I'll tell you, so there are different sort of numbers of customers. So you have some customers that have some demand, and you have some facilities that you can open. Each of those facilities have some particular configuration sizes, and you have to meet the demand of some number of products at each of the customers. So of course, the demand of the customers for a type of product is going to be the random variable. And for, we have, in general, we have some results in the paper where we have sort of like just a sort of a factor model, or it's just some sort of linear relationship, like you observe Eta, and then maybe there's some random noise, and this tells you what the demand is going to be. But just to make things really simple, and this is what some people have done in the literature, the simplest case is just imagine that Eta is equal to Cassie. They're sort of the same, they have perfect correlation. They have the same components. Just like if I decide to probe that customer, I will know exactly like how much of demand of each of these products that he wants. Sort of think of it like that, I think, is sort of the easy way to, and then we've done that for discrete distribution, done it also for continuous distribution. So the discrete distribution is just like the customer is either like really crappy, which is sort of like, this is the data distribution that's most relevant for the Exxon case, because often it's the case, they just want to know, is there really something there or not? It's like, did they open the box and like it's empty? Or do they open the box and they really got a big prize inside? And then but other cases, we did continuous distribution, and we actually have some results. I don't think I have any computational results where we just did a very sparse sort of correlation inducing model. Okay, so here we go. Yeah, this test. So it's stochastic facility location problem. In most of the results I'm going to show you, actually cheating, not really cheating, but it's just only the first stage was integer. But again, if you want to solve a 2-stage stochastic integer program by giving it to Gurobi that just has second stage integer variables, Godspeed. And this whole method will just work the same. But here it's just, we had continuous second stage, at least from the results I'm going to show here. But again, the non-anticipative myth is sort of like, even for the discrete distribution, is sort of out of the realm of comprehension in some sense. Okay, so I'm going to show you a few different computational results. So first I'm going to show you, like, we have sort of like let's call it the old way of sort of doing this decision-dependent uncertainty, where you have to enforce non-anticipative, or sorry, observation-dependent non-anticipativity, right? And I'm going to compare that to the information relaxation-based approach. I'll show you sort of some remarkable results I thought about. Like I alluded to the fact that like these R of A to S values appear all over the place. So if you're smart, if you have a discrete distribution, you can save yourself a lot of computation time, and the branch and bound tree could go faster. Branching rules. And then mostly what I show is like what bounds we can get using this, and try to make the case that these are actually very good, like really improving on the perfect information bound, which I think is hard to do in general. So it's hard for us to report so much about computation times because, of course, we're doing replication and sampling. All the bounds I'm going to show you are like statistical in nature, which is great because we have, like, in Wisconsin, Merivin knows, we have like many huge clusters of workstations that we're allowed to use, but they're shared resources, so I can't give you accurate CPU time. So all of our CPU times are going to be in like the total number of Gurobi work units. You can kind of think of a Gurobi work unit as 1 second. It's sort of, I think that's sort of reasonable to sort of do in this context. And so here's my first slide. It's the most Tada slide, I think, of the whole thing. So like here I'm showing you for some very small instances of the stochastic facility location problem, say with 6 customers and 5 facilities. If you can solve that non-anticipative 3-stage MIP using that method, and it takes like an hour, or you can use our method and it takes like 2 seconds, right? Or you can try it for 7 customers and you can't solve it, and the information relaxation solves it in 5 seconds. Right, and we can keep going, right? So we can solve much larger instances. As another example of that, you can take, I actually don't think that the problem, I don't think it really makes much sense in this context, but anyway, you could take a 20 scenario or a 20 customer instance with 5 facilities, and suppose your true distribution, we got this true distribution by sampling from a different distribution. But if your true distribution had 100 scenarios, you couldn't solve the MIP, but you can solve other information relaxation based solves in a reasonable amount of time. So that's like the most Tada, I think. So these slide. The other thing that I really sort of think is actually quite interesting is like how many scenarios. Oh, good question. So here in these scenarios, these are the true. So I should have said these are just the discrete distribution, and these are exact solutions, right? So this has 16 scenarios, 32 scenarios, 64 scenarios, 128, 256, 512, 1024, right? And then actually the true distribution has 1024. From that, we sampled 100 and solved that sampled approximation, whatever that means. This is the bound.
Sorry, how many uncertain parameters were there in these problems to understand?
Yeah. So this is this case. So this is the case where there were 10 uncertain parameters because there were 10 customers, and we're observing the customer. Oh, sorry. Observing the customer, but you observe everything about the customer. So there's a little bit of correlation. If there's one product, there would be 10 uncertain parameters. Or the 2 products, there would be 20 uncertain parameters, but you sort of would observe them both. Does that make sense?
And so when you say 64 scenarios, it would be still 64 for like.
Yeah, so each customer's demand is independent.
I see.
So that's where the scenario sort of comes from. And these instances that I'm showing you, that would be. And now I don't know if it's exactly for these, but just like when you're solving, these were discrete distributions. So you can do that. And this is an external sample, obviously. I just took 100 samples from the joint to sort of see like how fast or how many times do you actually have to solve a 2-stage stochastic integer program? Like you have to see that like you have to do the branch and bound trees. Unfortunately, you have to do sort of many nodes of the branch and bound tree. I would say. Like here, to completely evaluate that branch and boundary takes quite a while, at least in terms of number of nodes. But here, actually, like most of the time, you're just looking up the solution. Like it's some like huge, you tend to, if you just branch on one variable, you tend to be able to sort of the child node looks a lot more similar to the parent node, and so you really use a lot more of the same information than if you do this multi-way branching. But still, it's not, you still, even in that case, you reuse a lot of the computations. I have a couple pictures that, so this is the first one where this is from a continuous distribution. Oh, I really got to go quicker. Okay, so a continuous distribution is sort of showing the evolution of the upper bound or the branch and bound tree as a function of the number of Gurobi work units for the different branching methods. Here's one example of that. So you can sort of see for a fixed amount of work, this multi-way branching method tends to work better, especially for the continuous distributions. These are like 95% confidence upper bound. And then maybe I'll kind of almost end with this slide in the sense of, so I think this slide is more remarkable than it appears in that, so for these instances, to answer Phoebe's question, can say either 2 to the 20th or 2 to the 25th scenarios associated with them. These are from continuous distributions, okay? So if you do continuous distributions, you can't actually do better than what you would get from, this is our estimation of the perfect information bound. Here's the best solution to any of these instances we ever found. And like, here's what you can get, which is I would say some significant improvement over the perfect information bound for these classes of instances, which for continuous distribution, actually, I don't really know of any method that has been able to give sort of this kind of improvement over the perfect information bounds, like provable statistical upper bounds that are this much better than the perfect information bounds. These lower bounds we got from a heuristic. This is just sort of showing that. So it actually turns out this might be, I'll give, maybe 1 minute over, I apologize. There's some, because I think it's useful for like maybe this community to hear. There's this great paper from Shabir, who we all still terribly miss, about a 2-stage stochastic, say, integer programming, especially with a first-stage integer. If you do sample average approximation to solve that problem, and so you're doing lots of replications, like almost always, and this is my experience too, almost always one of those solutions you saw is from one of the replications of doing sample average approximation is either the optimal solution or very close to the optimal solution, right? So we did that same thing in this context. So for like a 25 customer problem, we took from so I guess that's coming from every different branching method, from every different sample size. We took every solution that came from that, and then we reevaluated the quality of that solution to get an unbiased estimate of its value. And we got the yellow distribution of solutions. And then from our heuristic, it generates a number of solutions, and we look at the 10 best and reevaluate them. And so our heuristic, this is just to show our heuristic is working well. But what I find even more interesting is that for these problems are significantly harder than 2-stage problems, that like none of the solutions we ever saw, these is like hundreds of different sample average solutions, was even close to the solution that we found by a simple greedy heuristic. Anyway, so I'll end there by just saying I don't believe in decision-dependent uncertainty. I hope you found it interesting, and sort of maybe you can use this sort of simple information relaxation branch and bound approach in your own work as well. So thank you very much. I apologize for running over, but I'm happy to take any additional questions, especially from Tito. Hi, Tito. Or Bernard.
Hi, Jeff. Well, since you asked me to ask a question, I do have a question.
No, I'm just kidding, yeah.
Nice talk. No, I was just wondering, I mean, here you're assuming everything, right? That you know the distributions, the joint distributions. So in case you don't know the conditional distribution and you need somehow to infer that from data, right? Do you envision a way of doing some learning procedure here to learn this dependence as you go?
That's a great point. Yeah, like we hadn't really thought of that, but that would be, and I'm trying to think of like maybe natural next extensions of like how to do that. Like, and this would be like a very natural one to do, to be like, yeah, just what if there's no way you can, these things exist, but like you can only sort of try to get better approximations of them as you go. Yeah, I don't know how that would impact these things, but Jim probably does. So I'll tell him that would be a good way, a good next problem to sort of think about, to sort of be like what that does to the types of bounds, you might be able to actually infer or get.
Thank you.
Great point.
Is
Any
Murphy
other
still
questions?
here? I'm not sure if Murphy is still here.
No,
We lost
she
her.
left in disgust. She left in disgust.
I can moderate if she's not here. Any more questions? I'll ask one more if when people are
course.
thinking. In the last set of experiments, Jeff, let's see, yeah, here. So yeah, this PI bound in the continuous distribution case is an estimate, or somehow it's exact.
No, this is an estimate. I didn't put the standard errors of this. Like we just had to, it's the standard errors of all of these things. It's pretty easy to get the variance of the estimates down a little bit with more work. Like you have to 1 over root n, but so I think the variance is like, or the standard error is like 10 or 12 or something. I can't remember. So like the 95% confidence interval is 20 or 30 higher than this.
Got it. Okay,
think-
yeah, very nice work, Jeff. Are there any more questions?
Well, thank you all for joining. I
Also-
appreciate it, especially seeing so many old friends and hopefully some new friends that I'll meet in Paris, if not before.
Thanks
Thanks a lot, Jeff. Thank you.
All right. Bye all.
Bye-bye.